Example: a stationary electromagnetic sheet. 45. It should be remembered that we regard the displacement and the induction as actual states of the medium, and therefore if the medium be moving, it carries its states with it. Besides this, it usually happens that these states are themselves being transferred through the medium independently of its translational motion, so that the resultant effect on propagation, considered with respect to fixed space, is a combination of the natural propagation through a medium at rest, and what we may call the convective propagation. Of course, we could not expect the two laws of circuitation for a medium at rest to remain true when there is convective propagation. The matter is placed in a very clear light by considering the very simple case of an infinite plane lamina of E and H traveling at the speed of light v perpendicularly to itself through a homogeneous dielectric. This is possible, as will appear later, when E and H are perpendicular, and their tensors are thus related. Force E equals mu v times H, or vectorizing v to v, E equals mu vector product HV. According to the definition of a vector product, gives the directional relations as well as the numerical. Now suppose we set the whole medium moving the other way at the speed of light. The traveling plane electromagnetic sheet will be brought to rest in space whilst the medium pours past it. Being at rest and steady, the electric displacement and magnetic induction can only be kept up by coincident impressed forces, that is, E equals E, H equals H. Now compare equation 8 with 5 and 6. Consider the directions carefully, and remember that the velocity q is the negative of the velocity v, and we shall obtain the formulae 5 and 6, which are thus proved for the case of plane wave motion, by starting with a simple solution belonging to a medium at rest. The method is, however, principally useful in showing the necessity of, and the inner meaning of the motional electric and magnetic forces. To show the general application of 5 and 6 requires a more general consideration of the motional question, to which we now proceed. Connection between motional electric force and electromagnetic force. 46. A second way of arriving at the motional electric force is by a consideration of the work done in moving a conducting circuit in a magnetic field. It results from Ampere's researches, and may be independently proved in a variety of ways, that the force of acting upon a conducting circuit supporting a current may be accounted for by supposing that every element of the conductor is subject to what Maxwell termed the electromagnetic force. This is a force perpendicular to the vector current and to the vector induction, and its magnitude equals the product of their tensors multiplied by the sine of the angle between them. In short, the electromagnetic force is the vector product of the current and the induction. Or, by the definition of a vector product, F equals vector product CB. If F is the force per unit volume, C the current, and B the induction. Here F is the force arising from the stress in the magnetic field. Its negative, say F, is therefore the impressed mechanical force, or F equals vector product BC. To be used when we desire to consider work done upon the electromagnetic system. The activity of F is Fq, if Q be the velocity, or by Fq equals Q vector product BC. This is identically the same as Fq equals C vector product QB. By a fundamental formula in vector analysis here, on the left side, the activity is expressed mechanically. On the right side, on the other hand, it is expressed electrically, as the scalar product of the current and another vector, which is the corresponding force. It is necessarily an electric force, and necessarily impressed. So, calling it E, we have E equals vector product QB. Again, to express the motional electric force. It should be observed that we are not concerned in this mode of reasoning with the explicit connection between E and C, and in this respect the process is remarkably simple. As it, however, rests upon a knowledge of the electromagnetic force, we depart from the method of deriving relations previously pursued. But, conversely, we may by equations 11 and 12 derive the electromagnetic force from the motional electric force.